Hey everyone! In this video, we're going to be taking a look at a couple more examples where we're going to be finding the area between the graphs of a couple functions. But in this video, what I want to look at is how there is always, or usually, more than one way that we can approach the problem. So my first example says find the area of the region enclosed by the graphs of y is equal to the square root of 4 minus 4x, y is equal to the square root of 4 minus just x, and the x-axis. So let's start, as we should usually do, by just sketching out a graph of our situation. So in both cases, for both of these graphs, they're the square root, but because it's the opposite of x in both cases, that means they're going to be reflected horizontally. So if we take a look at these, we can think about a couple points of intersection with the x and the y-axis to help just give us a general idea of the shape. So if I plug in 0 for both of these, so at x is equal to 0, the first one, we have 4 minus 0, so that's going to be the square root of 4 is 2. And for the second one, we have 4 minus 0, so the square root of 4, that is also 2. So for both of these, they're going to cross the y-axis at 2. And now let's think about where they're going to cross the x-axis. So we want our square root to be 0. So for the first one, if I plug in 1, I'll end up with 4 minus 4. So that's going to give me 0. So at 1, that's where that first one will intersect the x-axis. And then our second one here, if I want this one to be 0, I'm going to need to plug in 4 for x. That'll give me 4 minus 4, which is 0. So here's our second one. It's going to intersect at 4. And I should label this first one, let's say 1. So they're both going to cross the y-axis at 2. Our first one is going to intersect the x-axis at 1. And then our second one is going to intersect at 4. So we end up with a region that looks like this. As usual, it doesn't need to be perfect. We just want to end up with a situation that gives us a general idea of what we're working with. So now, the region that we want to find the area of is going to be this region that is in between these two graphs and the x-axis. So down y is equal to 0 here. So I have a couple ways I can handle this. The first one, let's think about how would we approach this if we were going to partition the x-axis. So our rectangles are going to end up being little vertical rectangles. So for example, here we'd have a rectangle that would look something like this. But then further down the line, we have a rectangle here that goes all the way down to the x-axis. So thinking about that, this first rectangle is the height of that is going to be the difference of the value on this blue graph subtracted with the value on the red one. But as I move along, the second rectangle I drew in here is actually just, we have a value up here on the graph in blue and the x-axis, and I don't actually need my graph in red at all. So if I want to partition this along the x-axis, I'm actually going to split this into two parts. And I'm going to split it up here at x is equal to 1. So for this region between 0 and 1, I want to take the area underneath my blue curve and subtract the area underneath the red curve. So the integral here underneath the blue one, that gives me the entire thing. And then I want to subtract away the area of this region in red here. And then once I figure that out, all I need to do is just add on the normal integral for our second function. And that will give me just this entire green area underneath our graph in blue and the x-axis. So to write that out, so for our first part, we're going from 0 to 1, and then we want to do a difference here. So the function that's bigger, the one that has the greater values, is going to be our second one. So 4 minus x. And then from that, we're going to subtract the one that's smaller. So our one here in red, which was our first one, which is the square root of 4 minus 4x. And closing that off, and then we have our dx. So that's going to give me the area of this little region here. So everywhere in between the blue and the red. And then to that, we want to add a second integral, which goes from 1 to 4 of just our graph in blue, which was our second one. So the square root of 4 minus x, and we have our dx. So this expression here, this splits it up into two parts. Our first one, we have the integral of our bigger one minus the smaller one, which gives us the area of this little piece. And then the second piece here that we're using is an integral from 1 to 4, and this is just a normal integral because that gives me the area underneath our curve up until the x-axis. Now let's just compare this to a second way that we can approach it, which would be partitioning along the y-axis. So in this case, we'd want to be looking at the rectangles that go horizontally, like this. So if we look at these rectangles, in this case, we can see that we want to take a look at the interval that goes from 0 up until 2, where they intersect again. So 0 because that's the x-axis, and then up at 2 because, like I said, that's the point of intersection. So if we take a look, splitting this along the y-axis, our rectangles we can see are going to be in between the blue and the red graphs everywhere on this interval. So that means we can just use one integral where we take a look at the difference between them. However, our two equations are written as a function of x. Right now it's y is equal to something. So what I need to do is I actually need to rearrange these so that they're a function of y. So I want to rearrange and rewrite so we have x is equal to something. So for that first one, y is equal to the square root of 4 minus 4x. Starting off, we'll square both sides. So y squared is equal to 4 minus 4x. And then we can subtract 4. So that's y squared minus 4 is equal to negative 4x. And to finish up dividing everything by negative 4, we get x is equal to, and let's see here, I'm going to do a negative 1/4 y squared plus 1. And just to keep things consistent, I'm actually going to take this and let's put this in red because this represents our function here that intersects at positive 1. So now let's do the same thing for our second one. So y is equal to the square root of 4 minus x. And in the same process, we just want to isolate x. So we have y squared. And then we can subtract 4, so y squared minus 4. And then multiplying everything by negative 1, we have x is equal to negative y squared plus 4. So now that we have these written in terms of x, or x is isolated and they're written as functions in terms of y, now we can figure out the integral. So our integral, so we want to go from 0 to 2. So again, we're partitioning the y-axis. So we're going from 0, which is the x-axis, is one of the borders that we wanted. And then we're going up to 2, where our two graphs intersect. And then we want to do the bigger one minus the smaller one. So the one in blue, this was our bigger one. So that's our second equation here in terms of y. So negative y squared plus 4. And then we want to subtract our smaller one, which is this one in red. So here we have negative 1/4 y squared plus 1. And we have dy. So just comparing the two, if we wanted to partition the x-axis, we needed to split it up into two parts. The first part, because we have both of our functions exist within that interval. And then the second integral we had was because on that interval, the only thing we were concerned about was this function y is equal to the square root of 4 minus x. Our other option was if we rewrite our two equations and we write them as functions of y. So x is equal to something. Now we were able to use just one integral. In this case, we're going from 0, which is the x-axis, up to 2, which is where they intersect. And then we were able to write this as just the difference of these two functions. So taking a look, I think both of these are okay. And I'm actually just going to evaluate the second one just so we can see what the answer would be. So let me simplify inside the parentheses a little bit. So we have our integral from 0 to 2. And let's see, so distributing that negative, this is going to turn into positive 1/4 y squared. So negative 1 plus 1, so that's going to be 3/4, negative 3/4 y squared. And then we have positive 4 and minus 1, so that'll be plus 3. And we have our dy. So then using our antiderivative rules, so let's see what we end up with. So this is going to go up to y cubed, and then we're going to divide by 3, which would cancel out with the 3 and the 3/4. So I'm going to leave a negative 1/4 out front. And then the antiderivative of 3 is 3y. And this we're going to evaluate from 0 to 2. I'm going to scroll down a little bit to give myself some room. And then plugging in our upper and lower bounds. Negative 1/4 times 2 cubed plus 3 times 2. And plugging in 0, both terms will be 0. So we don't have to worry about that. So let's see what we get. 2 cubed is 8. And then negative 1/4 times 8, that's going to be negative 2 plus 6. So in total, we end up with an area of 4. Now, if we were to go back up here and evaluate these two integrals, we should end up with the same answer. So this just goes to show that there is more than one way that we can approach a problem. Sometimes partitioning along the x-axis is easier than partitioning along the y-axis, or vice versa. So it is valuable to think about both situations. So now let's take a look at our second example, which illustrates that point a little bit further. So the second example says, find the area of the region enclosed by the graph of y is equal to the natural log of x, the x-axis, and the vertical line x is equal to e. So again, let's just start off by sketching this out to see what we have. All right, so let's start off by thinking about our vertical line x is equal to e. So e, the irrational number, is about 2.71. So let's draw in a vertical line here at e. So something like this. So that's one of the borders of our region. Another one is the x-axis, so that's easy. And then now let's think about our last one, which is y is equal to the natural log of x. So it's a logarithmic graph, so we know that it's going to have a vertical asymptote at the y-axis. So we can't plug in 0 because the natural log of 0 is undefined. But at 1, we know that that has a value of 0. And then if I think about where it's going to intersect my vertical line, I can plug in e. The natural log of e is actually just 1. So it's going to intersect here at e, and then the y value is positive 1. And it's logarithmic, so it's a nice smooth curve that goes over to here. So the area of the region we want to find is underneath our logarithmic graph, down to the x-axis, and then up until our vertical line here at x is equal to e. So taking a look at this, just at first glance, it seems like we should be able to find the integral. So we're going from 1 to e, and then the graph we have here, so this is the graph of y is equal to the natural log of x. So it looks like we should be able to just do the definite integral from 1 to e of the natural log of x times dx, which would be great, except we actually don't know how to find the antiderivative of the natural log of x. Well, we don't know how to find it yet. We will eventually, but not right now. So because of that, we can't partition this along the x-axis. So instead, we're going to want to partition this along the y-axis. So we have our intersection here at 1, and we have the x-axis as another one of our borders. So if I partition this along the y-axis, my two bounds are going to be 0 and 1. One of my equations is already in terms of x is equal to something. So x is equal to e. So that gives me this function here. But I need to take my second one, y is equal to the natural log of x, and we need to isolate the x so that this is a function in terms of y. We can do that just by rearranging this. So natural log is base e. So this equation, this is equivalent to x is equal to e to the y power. So now, partitioning along the y-axis, looking at our little horizontal rectangles, we're going to have an integral from 0 to 1. 0 because the x-axis, 1 because that's where these two functions intersect. Now let's take the bigger one. So our bigger function is just e. And we want to subtract the smaller one, which is our one in blue, which is going to be e to the y power. And we have our dy. So in this case, it looks like we can just do a normal definite integral, but because I don't know the antiderivative of natural log, I don't know it yet, because of that, we can switch and we can think about partitioning this along the y-axis, and we can still find something that we can evaluate. So let's use our antiderivative rules and see what we get. So this is a constant, so the antiderivative to that is going to be e times y. And then the antiderivative of e to the y is itself. And we want to evaluate this from 0 to 1. So let's see what we get. So plugging in the upper bound of 1, e times 1 minus e to the first power, which is e. And then we'll subtract, plugging in our lower bound. So e times 0 is going to be 0, and we have minus e to the 0 power, which is 1. So it looks like we got a lot that simplifies. E minus e is 0, and then we're going to subtract. So that's going to be negative 1. So minus a negative 1, we're going to add 1. So in total, we end up with just positive 1. So that means the area of our region here bounded by the graph of y is equal to the natural log of x, the vertical line x is equal to e, and the x-axis, this area is exactly 1 unit. So in this example, I just wanted to show that sometimes the initial thought, in this case, a regular definite integral, isn't always the easiest option to take. In this case, we didn't know how to find the antiderivative of the natural log, so that made us start thinking about different ways we can approach it. So then we thought about what if we partition it along the y-axis, and we were able to come up with an integral that will give us that value. In the first example, both options, partitioning along the x-axis or partitioning along the y-axis, were both viable options. However, maybe one of those is easier than the other, so overall it's always a good habit to get into to think about both ways. If I partition along the x or if I partition along the y, and sometimes one of those is going to jump out at you as the better way to approach the problem.